So last time we defined a topology on a set X by declaring which subsets we want to be open as long as they satisfy our three rules. But in general, this kind of sucks. For example, let's say I want to give R the regular old standard topology. In other words, open intervals are open sets. But there are more open sets than just open intervals. For instance, a disjoint union of two open intervals is open, as are 3 or 10 or infinitely many. How are we supposed to declare all of them? Verifying that this is indeed a topology becomes, well, not impossible, but very unwieldy, because a generic open set in R isn't just a single open interval. And so making sure that all three rules of the definition of a topology are satisfied for a generic open set becomes like a mess of decomposing into like disjoint open intervals. That's not even considering the fact that we should probably be careful even attempting such a thing, since we probably don't have a great intuition for topologies at this stage, and so our proof might appeal to a couple of course it must be so's, which is never a good thing. Furthermore, what if we're dealing with some horrendous pathological example that's nothing like R? Maybe listing every possible open set is just impossible to do. In fact, our topologies don't even have to be pathological for that to be the case. What are we to do then? That's where bases come in. A basis is just a way to describe a topology on a set, without having to just declare every possible set that's open or not. Here's the definition. A basis for some topology on X is just a collection of subsets of X, call it B, whose total union is all of X, and whenever a point little x in X is in the intersection of two basis elements B1 and B2, then there's a smaller basis element, B3, which contains X and is contained in the intersection of B1 and B2. We say that B3 is sandwiched in the intersection if we're feeling froggy. Truthfully, the specific open sets of your topology really don't matter all that much. We're usually much more concerned with the properties of the topology. What separation axioms does it satisfy? What do continuous functions in and out of it look like, etc. A basis is just the acknowledgement that here's enough information to declare a topology, now let's start to focus on the things that really matter. So we're going to do just enough work to demonstrate that bases do what I claim they do, namely generate topologies, and then we probably won't refer to bases explicitly that often in the future. So, here's our first theorem. If B is a basis on X, then the collection of all U, which are subsets of X, such that for every X in U, there exists a basis element B, such that X is an element of B contained in U, is a topology on X. Suggestively call that collection tau, right? We say that B generates tau. Like last episode, we'll appeal to the definition of a topology. First, the empty set is in tau vacuously, and X is in tau because of this. For closure of arbitrary unions, if we have a mess of U sub alphas in tau, whose union is U, then let X be in U. That means X is in U sub alpha naught for some alpha naught. And since U sub alpha naught is in tau, that means there exists some B in script B, such that X is an element of B contained in U sub alpha naught, which is contained in U. So that means U is indeed in tau. For finite intersections, we show that the intersection of two sets is in tau. Finitely many can be achieved via a process called induction. So let U1 and U2 be in tau, we need to show U1 intersect U2 is in tau. If we let X be an arbitrary point of the intersection, then since U1 and U2 are in tau, that means there exists a B1 and a B2, which are basis elements, such that X is contained in B1 inside of U1, and X is contained in B2 inside of U2. Since X is contained in both B1 and B2, and B is a basis, then that means there exists a B3, which is sandwiched in between the intersection of B1 and B2. In other words, X is an element of B3, which is a subset of B1 intersect B2, which is a subset of U1 intersect U2. Thus, U1 intersect U2 is an element of tau. There is another way to characterize a topology tau generated by a basis B. Consider it homework to show that U is open, i.e. U is an element of tau, if and only if U is the arbitrary union of basis elements. A hint, one direction is easy, and the theorem we just did proves the other direction. You could also figure out a basis given a topology. But why? We already said that bases aren't the point, they're just a means to an end. Consider it extra credit worth -5 points, because we're keeping track of points now. The real meat and potatoes of bases is that we've solved the problem of having to list every possible open set in order to have a topology. Instead, we specify a basis, and it generates a topology. Let's see what I mean. Take B to be the collection of all open intervals in R. Then B generates a topology known as the standard topology, the default topology you know and love, where open sets in the topology are just the open sets from calculus. This is clear once you've proven your homework. An open set is a union of open intervals, so B generates exactly the thing it's supposed to. To check that this is indeed a basis, well, we know that R is the union of its open intervals, and if you hand me two open intervals that overlap, then I can sandwich an interval in between their intersection. Thus, ta-da, we have a basis. For a different example, we could let the basis be the collection of all intervals which are closed on the bottom and open on the top. This generates what's known as the lower limit topology on R, and I'll admit it seems like a minor change compared to the standard topology on R, but it actually has some strikingly different properties. I mean, right now you have to trust me because we don't know any properties of topology, but if we let K be the set of the reciprocals of natural numbers, then we can define a basis B by being the collection of open intervals or open intervals minus K. This generates the K topology on R. Some screwy things happen around 0 in this topology. But bases don't just give us topologies on the set of real numbers. Like we said at the start, defining a topology from first principles is hard, because we have to declare open or not for every possible subset of our space X. But checking if I have a basis is a relatively easy criterion. We've just got to check that it unions to X and that sandwich property. So from here on out, pretty much every topology we're going to build either comes from a basis or is built from existing topologies that we already have. So let's define some more topologies so that we have a collection of examples. If X is a simply ordered set, that just means that you can hand me any two elements and I can tell you which one is bigger. That means that we can build intervals. Open, closed, half open on one side or the other. Here's a basis on X, and you should check that it is. B is the collection of all open intervals AB, all closed on the bottom intervals A0, B, where A0 is the least element of X if it exists, and all closed on the top intervals A, B0, if B0 is the greatest element of X, if it exists. We say that B generates the order topology on X. If X is R, then the order topology is just the standard topology. That's immediately evident because the bases are exactly the same. But the order topology can give new examples too, if we just choose sets other than R. Here's an example. Let's let X equal 1, 2 cross n. So that means elements of X are ordered pairs, where the first coordinate is either 1 or 2, and the second coordinate is any natural number. And for us, n starts at 1. We're not heathens, for God's sake. Now we can give X a simple ordering, called dictionary order, or lexicographical ordering if you're compensating. Basically, put things in dictionary order. So we put things in order according to the first coordinate. But if the first coordinates agree, then we put things in order according to the second coordinate. So, for example, 1, 3 is less than 1, 19, which is less than 2, 4, which is less than 2, 30. So we have an ordering on X, and thus we get the order topology on X. We actually don't know too many topologies on X. In fact, right now we only know the discrete, trivial, and finite complement. It's clear, by which I mean convince yourself, that the order topology hasn't given us the finite complement or the trivial topology. So all that we need to do to show that the order topology is something genuinely new is show that it's not the discrete topology. And to do that, all we have to do is come up with a single set which isn't open. For us, we'll do that with the singleton 2, 1. So why is 2, 1 not open? Well, let's write X in dictionary order so that we can see what open sets containing 2, 1 look like. If we stick an open interval, which I will remind you is an element of the basis of the order topology, around 2, 1, then it has to contain 1, n for all n sufficiently large. This is unavoidable, so the singleton 2, 1 can't be open because it doesn't contain 1, n for a large n. Thus, the order topology on X is not the discrete topology either. There are many more topologies that you can build by constructing their bases. This includes actual important examples, as opposed to the kind of quirky example we just did, so we'll keep bases in our back pocket. Let's end today by talking about another topology, the subspace topology. The name is pretty self-explanatory. A subspace is just a topology that sits inside of a larger space. Since we've already began to conceptualize topologies as describing nearness via their open sets, that means that the subspace is going to describe the same sort of nearness that the superspace does. If you have that in mind, the following definition is completely evident. If we have some topological space, X, and Y a subset of X, then we can give Y the subspace topology with respect to X by declaring all of the open sets of Y to be those that come about by intersecting Y with an open set of X. In terms of a basis, we can do the exact same thing. It's not too hard at all to show that if you have a basis for your space X, then we get a basis for the subspace topology on Y by intersecting every basis element with Y. And of course, if you prefer thinking about closed sets, it's completely equivalent to say that every closed set in a subspace Y comes about by intersecting Y with a closed set in X. Pictorially, which once you internalize the rigor is the right way to think about this, subspaces are super easy to visualize. If here is a space X, then a subspace Y is here, for example. And if this is an open set of X, then the corresponding open set of Y is this.